Identities! We're going to be looking at some more of them. We previously looked at the reciprocal and quotient identities, where we introduced our secondary trigonometric functions. Today we'll be looking at the Pythagorean identities. These are based on the unit circle, which states that x squared plus y squared equals 1. But we also know that on the unit circle, x is equal to cosine theta and y is equal to sine theta. So when developing our first Pythagorean identity, we start with that unit circle. So on the unit circle, how do you draw an x? Not like that. X squared plus y squared is equal to 1. And what we know is that x is the same thing as cosine theta, and y is the same thing as sine theta. So we can replace them just like that. In simplifying this, cosine theta being squared is just written as cos squared theta. And sine of theta being squared is just written as sine squared theta. And this right here is the first Pythagorean identity. No matter what the value of theta is, it'll always be true that cos squared theta plus sine squared theta is equal to 1. Now we can also represent this in some alternate forms. And it's not necessary to memorize these forms, but just recognize that we can manipulate this formula a little bit. Like if we subtract cosine squared from both sides, then we're going to get that sine squared theta is 1 minus cos squared theta. And in a similar sense, we could instead subtract sine squared theta from both sides, and we get that cos squared theta is 1 minus sine squared theta. Again, you don't have to commit these to memory, but do recognize that they exist and that they are just variations on this first identity here. That one, I believe, is on your formula sheet, so you will certainly want to have your formula sheet handy, unless you memorize these, which is also very valid. There are two other identities we can develop as a result of having this. And we are, for those, going to be using our knowledge of how to convert into the secondary trig functions. So starting with this business that we have cos squared theta plus sine squared theta is equal to 1, there are a couple things we can do with that. One thing we can do is just say, you know what, I think I'm going to divide every single term by cos squared theta. What does that do for us? Well, cos squared theta divided by cos squared theta is 1. Now sine over cos is tan, so sine squared theta over cos squared theta is tan squared theta. And 1 over cosine of theta is just secant of theta, so 1 over cos squared of theta is is just straight up secant squared of theta. This is the base identity itself, but as with the others, we can manipulate this to have alternate forms. Whoop, how do these random things get in there? So we can represent this in other ways as well. If we want, we could subtract tan squared theta from both sides. On the left side, that leaves us with 1. And on the right side, that means we have secant squared theta minus tan squared theta. Alternately, from this original form here, we could subtract 1 from both sides, so that on the left we have tan squared theta, And on the right, we have secant squared theta minus 1. So that's one way we can manipulate this original Pythagorean identity to get something else based on other trig ratios or trig functions. But we can manipulate that another way too. Whoop. Again, starting with the fact that cos squared theta plus sine squared theta is equal to 1, instead of dividing things by cos squared theta, we can divide instead by sine squared theta. And that's going to happen to every single term. What happens there? Well, cos over sine is cotangent, so cos squared theta over sine squared theta is cotangent squared theta. Sine squared theta over sine squared theta is equal to 1. 1 over sine theta is cosecant theta, so 1 over sine squared theta is cosecant squared of theta. And that is our third Pythagorean identity. We can manipulate this one as well to get some alternate forms. If we take our original expression and subtract 1 from both sides, then on the left we just have cotangent squared of theta, and on the right cosecant squared of theta minus 1. Or from this version up here, we can subtract cotangent squared theta from both sides. On the left, that means we just have 1, and on the right we have cosecant squared theta minus cotangent squared of theta. So we have some alternate ways of looking at this, all just manipulations of what we originally had. But our three key Pythagorean identities are this first one up here, cos squared theta plus sine squared theta equals 1. This next one here, where 1 plus tan squared theta is equal to secant squared theta. And then this last one here, cotangent squared theta plus 1 equals cosecant squared theta. And you will see a version of each one of these on your formula sheet. So again, make sure it's handy, but do also make sure you recognize that it could be changed into any of these alternate forms. And it's not even just limited to those. There's a variety of ways to see how these are expressed. We're going to be using these identities, along with the ones we saw previously, our reciprocal and quotient identities, to manipulate even more complex trig expressions. And when we do so, our target might be to find some expression that looks like one of these, or one of these, or one of these, somewhere in whatever expression we are working with. And that could require factoring, or could be require just switching things around in what order they're listed. There's a variety of options, and we'll have to see what we could possibly do. Let's start with this one. Whoa! There's a lot going on there. We're going to try and express this in terms of only one primary trig function. So we're expressing these in terms of just sine or cosine or tangent. Only one of the primaries. What could we possibly do here? There's a variety of options. Everything here is already in a primary function. But where do we go? I see a sine squared. I know there's a relationship between sine squared and cosine squared and 1. Maybe that could be used to our advantage. Alternately, I'm noticing that on the top, I've got tan x and tan x. There's a common factor of tan x in the numerator. So what I'm going to do is factor that out. I'm going to say that what I've actually got on the top is tan x times 1 minus sine squared x. And the bottom is just cosine of x. So I got that by factoring. What we would hope to recognize now is that we've got 1 minus sine squared x. And that is an alternate form, or it's a rearrangement or a manipulation of this first trig identity. There's a relationship between 1 minus sine squared x and cosine squared of x. So by that knowledge, I'm going to mess around with this some more. I'm going to say that I've got tan x times cos squared x all over cos x. And again, this is because of that first identity. And that's because sine squared x plus cos squared x is equal to 1. This still isn't quite one trig function, but we've got cos squared x divided by cos x. So we condense it a bit more. Still not, oops. Common mistake actually, but make sure your variable stays there. So tan x times cos x. Still not one trig function. So I'm going to have to do a bit more with it. And I might consider representing tan as sine over cos. And now I can see that I can get rid of these cos x's and just write sine x. So that whole complex convoluted expression at the beginning, this tan x minus tan x sine squared x, all divided by cos x, is actually equal to sine x. This is considered an identity to say that this is equal to that, or to say that it's equal to any of these other steps along the way. That is considered an identity. Of course, that identity is only true over the permissible values of the variable. So it's not always true. It won't be true whenever cosine of x is equal to 0, whatever values cause that, because that will cause this whole fraction to be divided by 0. But whatever values of the variable are permissible, this identity will hold true. Whew, that wasn't a doozy at all. Let's try the other two. Give them a go. Try them out, see what you can do. There's, again, a variety of options with any single one of these, but explore them, see where you can convert, see where you can rearrange and manipulate algebraically, and continue with it until you manage to get these expressions down to just a single trig function, a single primary one. So please try it, give it a go, and then of course after you've paused, tried it, resume this video where I am continuing this one. I'm going to make two changes at once here. On the top, I'm going to expand and simplify that. That's essentially the factorization you get from a difference of squares. So I know that my result is not going to have any middle terms. It's just going to be cosecant squared x minus 1. If you want to work that out on scrap paper on the side, go for it. That's up to you. This bottom is 1 minus sine squared x. And I just used 1 minus sine squared x right up here. I just said it's actually equal to cos squared x. I'm going to use that same idea right here and say that we've got cos squared x. Boom, wicked. This thing already looks a whole lot nicer. What can I do with this? I've got cos squared x, that's all good and well. Cosecant squared minus x. There's a variety of things we can do with that. We can convert it if we want. We can say cosecant squared x is 1 over sine squared x, and we can work from there. If you do that, you will still eventually get the right answer. So that might be worth exploring. Personally, I might consider one of the Pythagorean identities again. And I'm specifically looking, not at that one, at this one. So, if I have cosecant theta minus 1, that's equal to cotangent theta. I'm not dealing with thetas here, I'm dealing with x's. but the rule's still the same. Cosecant squared x minus 1 is equal to cotangent squared of x. And the bottom, I made no changes. My next step from there, well, cotangent isn't a primary, so I'm going to express it as a fraction of primary functions. It's cos squared x over sine squared x. And that's all being divided by cos squared x. So there's the rationale there. There's the justification for it. And if I want to simplify this, I could do this in multiple steps if I want. I'm dividing by dividing by cos squared x over 1. What's that going to get me? That's going to get me 1 over sine squared x. And yes, we could convert this into cosecant squared x, but the thing is, that's not a primary trig function, and we were specifically asked for a primary trig function, so sine, cosine, or tangent. So we don't actually want cosecant x there. We can leave it as 1 over sine squared x, because that is a primary. This last example. Whoa! That is intense. I can do things with 1 minus cos squared of x, but not with 1 minus cos x, where this is just a power of 1. That kind of throws a wrench into things. Yoicks. Examining my options, I still have a bunch. Like I could maybe convert all these cosines into 1 over secant if I want. That's an option. What I might consider, and something I actually tend to consider whenever I see 1 minus a function or 1 plus a function, is to perhaps consider a way to combine these. And here we've got a fraction, another fraction. The way to combine two fractions is, or through addition or subtraction, is to make sure that they have a common denominator. So for me, I'm going to take this first fraction and I'm going to multiply it by the denominator of the second fraction so that I can start making my way towards a common denominator. And similarly, I'm going to take that second fraction and I'll multiply it by the denominator of the first one. And that way, my denominator will be 1 plus cos x times 1 minus cos x. So I'll have a common denominator, which is extremely handy. I don't have to turn these all into one giant fraction right now. I'll still take some steps here. So distributing this cos x, I can draw some liney lines like that. I'll be distributing that one as well. On this first bit, I'll have cos x minus cos squared x all over this product, 1 plus cos x times 1 minus cos x. And I'll be subtracting this next fraction. Again, distributing. Now we've got cos squared, not cos squared, just regular cos x plus cos squared x all over 1 minus cos squared x. Now I can turn these into one term. We have got cos x minus cos squared x minus the numerator of that second fraction. And that's all being divided by 1 minus cos squared x. Whew. Okay, I swear we must be getting somewhere. Condensing that numerator cos x minus cos x is nothing, but I do have negative cos x minus cos squared x. Sorry, phrase that wrong initially, but negative cos squared x minus another cos squared x. So I've lost 2 cos squared x's on top. And the bottom is 1 minus cos squared x, and I should be able to recognize that as being the same thing as sine squared x. So that's because, again, sine squared x plus cos squared x is equal to 1. Finally, I'm noticing that I've got cos squared x over sine squared x, and I know that that is equal to cotangent squared of x. So since cos x over sine x is equal to cotangent of x, cos squared over sine squared gives us cot squared. We are not in terms of a single trig function. It looks beautiful. This is very pretty, but it's not a primary trig function. So just to convert that, we would have to make sure that that cotangent squared turns into a tan squared, like so. And now this one is done. Let's put a nice little end of proof thing there. It's also called a square. But this way you look real mathematically professional. So that's that. That's these 3 complete. We have managed to express each of these in a single primary trig function. Boom, done. Looks pretty great. It can be complex and it can be challenging trying to see what to work with and how to work with it, which steps to pursue, because there are many, many possible steps that you could possibly pursue at any given point during any of these steps. So to get used to it, do make sure you do this practice. It is extremely necessary that you do that practice and you gain that familiarity, but it is also necessary that you ask questions. So please do reach out to me if you have questions, comments, concerns while working on any of this. Just make sure that any points of confusion or unclarity are cleared up, and that way you'll be at your strongest possible point so we can progress on to the next part of all this, because it just keeps ramping up. So let me know again if you have questions, comments, concerns. I will be here to assist you. But do the practice work, and believe in yourselves, and believe in the dream. Tell everyone that I say hello. Jason Thide out.